So in this video, let us look at the salient features of the graphs of polynomial functions. So till now we have discussed polynomial equations. Now we introduce a new concept called polynomial functions and discuss the relation between this function and the equation. So let us take a simple example. So let us take a polynomial equation f of x is equal to 0. So let us take an example x square minus 5x plus 6 is equal to 0. This is a quadratic polynomial equation. Now corresponding to this equation, this is my f of x. If I define a function y is equal to f of x, this is called a polynomial function. That is, y is equal to x square minus 5x plus 6. So this is called a polynomial function. A polynomial equation has solutions. A polynomial equation has solutions or roots. So we solve a polynomial equation and get the solutions of the polynomial equation or roots of the polynomial equation. But we don't solve a function. A function is some sort of a rule which connects x to y. We substitute different values of x and you get different values of y. A function is some sort of a rule which connects x to y. So a function has a graph. An equation does not have a graph. An equation has a solution. An equation has roots. A function does not need to be solved. A function is some sort of a rule which connects x and y. A function corresponds to a graph, and f of x is equal to 0 is an equation, y is equal to f of x is a function. Now if you draw the graph of this polynomial function, this is an example of a polynomial function. This is a quadratic. You can have any degree polynomial function. So one of the first thing that you need to observe about polynomial graphs are that the graphs of polynomial functions are continuous. That is, the graphs don't break anywhere. They go continuously without breakages. They go continuously without breakages. Second, as x tends to plus or minus infinities, as x tends to plus or minus infinities, f of x or y also tend to plus or minus infinities. So as x goes to infinities, y's also go to infinities. They can go to plus infinity or minus infinity anywhere, depending on the leading coefficients and the powers of the leading coefficients and the degree of the equation. So depending on leading coefficient and degree of f of x. This is the second thing to observe. So as you can very clearly see here, if x tends to infinity, at x is equal to infinity, these two terms will not matter much. Only the highest power of x matters. As x tends to infinity, y tends to infinity square, which is infinity. If x tends to minus infinity whole square is again equal to plus infinity. That means as x goes to minus infinity or plus infinity, y goes to plus infinity. The third thing to observe is the relation between polynomial equation and the polynomial function. The roots of polynomial equation, the values of x where f of x is equal to 0 are the abscissa of points where the graph cuts x-axis. Because if this graph cuts x-axis, that means y is equal to 0, and the values of x where this y is equal to 0 are nothing but the roots of this equation. X square minus 5x plus 6 is equal to 0. So wherever that happens is the solution of this equation. So the roots of f of x is equal to 0 are nothing but the abscess of the points where the graph cuts x-axis. For example, if you take this, the roots are 2, 3. At x is equal to 2 and x is equal to 3, y will be equal to 0. That means if you draw the graph of this, this is 2, this is 3. So 2 and 3 will be the abscess of the points where this graph meets x-axis. So the graph will look something like this. The graph goes to plus infinity as x tends to minus infinity as well as plus infinity. And they meet x-axis at the points which are roots of this equation. So the roots of f of x is equal to 0 are abscess of the points where the graph cuts x-axis. Next property is that if at 2 points A and B, let this be the point A, let this be point B. If at any 2 points A and B, the sign of f of x changes. So if between any 2 points the sign of f of x changes, that means if f of A times f of B is negative. If f of A times f of B is negative. That means if f of A is positive, f of B is negative, or negative positive. So if at A and B, the values of f of A and f of B change sign, then how should the graph look like? So if f is positive at A and negative at B, so what are the different possibilities for graphs between A and B? Because the polynomial graphs are continuous, they have to be continuously moving from this point to this point. So the graph can go like this. That means it has to cut the x-axis at some point between A and B. Or the graph can be something like this. It can go down, go up, and then come down to this point. That means the graph is cutting the x-axis at 3 points between A and B. Or it can move like this. That means the graph is cutting the x-axis at 5 points between A and B, or 7 points, or 9 points, so on. So if f of A into f of B is negative, then there should be odd number of roots to f of x is equal to 0 between A and B. So between A and B, f of x is equal to 0 should have odd number of roots, that is 1 root or 3 roots or 5 roots, so on. Similarly, if A and B are 2 points such that the sign of f of x don't change between A and B. If the sign does not change, means if you have a point A and a point B, so this is f of A and this is f of B. So what might happen between A and B? The graph is continuous, it does not get broken at any point. So the graph can directly go like this, where you don't have any root between A and B. Or it can come down and go like this, where it has 2 zeros between A and B. It can come down, go up, come down, and then go up here, which means that there are 4 roots between a and b, so on. So if the sign does not change between a and b, that is f of a into f of b is greater than 0, this implies f of x is equal to 0 has even number of roots between a and b. So I hope this statements are clear. If f of a and f of b have opposite signs, then there should be odd number of roots between a and b. If f of a into f of b is greater than 0, then there should be even number of roots between a and b. So next, there is a theorem called Rolle's theorem, which says that between any 2 roots of y is equal to f of x. So if you have a polynomial function y is equal to f of x, and if you have 2 numbers a and b, where f of a is equal to 0 and f of b is equal to 0. That means if the graph passes through these 2 points, then between these 2 points, f dash of x will be equal to 0 at least 1 point. So if a and b are the zeros of y is equal to f of x, or a and b are the roots of f of x is equal to 0, then f dash of x will be equal to 0 at least once between a and b. That means if you draw the graph between a and b, the graph has to go up and come down, right? So f dash of x will be equal to 0 at least 1 point somewhere in between a and b. It can be 0 more than once also. So if you have a graph which looks like this, it is 0 at this point, 0 at this point, 0 at this point. So if you can have more peaks and more troughs, you can have more number of solutions to f dash of x is equal to 0. So between two zeros of the function f of x is equal to 0, between 2 roots of the equation f of x is equal to 0, f dash of x will be equal to 0 at least once, or more specifically odd number of times. At least once between a and b, or more specifically odd number of times between a and b. So either once or 3 times or 5 times or 7 times, so on. So this is called Rolle's theorem. And a corollary to this theorem is that between 2 consecutive roots of f dash of x is equal to 0, between 2 consecutive roots of f dash of x is equal to 0, f of x is equal to 0 has at most 1 root. F dash of x is equal to 0 has at most 1 root between 2 consecutive roots of f dash of x is equal to 0. That means, let us say that f dash is equal to 0 at a and b. That means the tangent is parallel to x-axis, or the graph becomes flat at these 2 points. Assume that the graph becomes flat like this, and the next consecutive root is like this. So you cannot have 2 consecutive maximas. So here, if it is maxima, the next consecutive root should correspond to a minima. So if the graph is like this at a and like this at b, if you connect these two, because b is a and b are consecutive roots of f dash of x is equal to 0, in between a and b, f dash of x is not equal to 0. So they have to get directly connected. So here, as you can see, there is no root for f of x is equal to 0 between a and b. In the next case, if at x is equal to a and x is equal to b, the graph is like this at a, and the graph is like this at b. And in between a and b, f dash of x is not 0, and it directly goes down and meets this trough. Here, as you can see, f dash of x is equal, f of x is equal to 0 has exactly one root between a and b. So these are the only two cases which are possible. So if you have two consecutive roots of f dash of x is equal to 0, between a and b, there can be at most one root for f of x is equal to 0. Right? And when will you get a root and when will you not get a root? So if both these f of a and f of b are of same sign, then you won't get any root between a and b. If f of a and f of b are of opposite signs, then you get exactly one root between a and b. So between two consecutive roots of f dash of x is equal to 0, f of x is equal to 0 has at most one root. And more specifically, no root if f of a into f of b is positive. That means both at a and b, f has same sign. And one root if f of a into f of b is negative. So I hope this is clear. If f dash of x is equal to 0 at 2 points, such that these 2 points have the functional values of opposite signs, then you have exactly one root between a and b. If both are of same sign, both are positive or both are negative, if you join like this, both are positive and both are negative, then also you won't have any root between a and b. So this is a very powerful theorem which can be used to see how many real roots a cubic equation has.